Welcome to Maths with EJD. I've been making a series of videos on basic calculus, and I've started making videos on applications of differentiation. In the last video, I talked about applications of differentiation to kinematics, which talks about motion without worrying about the forces causing the motion. So in this video, I'll be talking about applications of differentiation in the area of linear approximation. This is simply, with this, you can actually estimate expressions, formulas, and all that, using derivatives approach. And of course, derivative, as you know, is about differentiation. Okay, so let's go to that. When you talk about linear approximation, right, this is the kind of thing we talk about. So the equation of the line, so it's more like you have an expression, you have a function, right? And you want to use it you want to approximate it at a particular value. So the equation of the line tangent to the graph of the function f of x. Now you see this is a function, the function in red is a function f of x. It looks like a parabola kind of. And then the equation of the line tangent to the graph, you see this blue line is tangent to it. A tangent is actually a line that just touches a curve at a single point, right? So the equation of the line tangent to the graph of the function f of x at a point a comma f of a is defined by this slope. So you know the equation of a straight line is like you have y equals, okay, well, maybe one other way to have it is you can say y minus y1 over x minus x1. That's like slope, and that is equal to m. If you know the slope and you know all these other things, you can quickly formulate an equation from it. So in this case now, the y1 is now like your f of a, while the x1 is like the a itself, the independent variable, which leads to the dependent variable f of a. So you have the slope y minus f of a all over x minus a equals f prime of a, such that you can get your y. If you can resolve this, multiply both sides by cross multiply rather, so you have f prime multiplied by f prime of a multiplied by x minus a, and then you can transfer f of a to the other side. So that's why your y is f of a plus f prime of a equals x minus a. So you see with this now, it's more or less like you're applying differentiation here to get an expression for y, right? Maybe you want to know the value of y for a particular function at a given point a comma f of a. So your y can be approximated this way, and you see derivative coming in here. So without the derivative, it's not complete. So that's why we apply differentiation in linear approximation. So this can be used to estimate the value of f of x for x close to a. So for any x close to a, you can approximate the value of the function at the given value a. All right. So that goes. And then we can take particular examples as we go to slide 11. Okay. So here, example 1, find the linearization of f of x, which is 1 over square root of 1 plus x at x equals 3. So we want to find the linearization of that function. Now you can see the function itself is not a linear function. It is not a line. So a linear function is that function that has just the maximum power is 1, like maybe 2x plus 3. But this one, if you plot it, you see that it's not a straight line. It can be a straight line. So this is linear, for instance. So linearization is more like you approximating the function you have. Okay, and just like we know, right? Just like we know, we already have an expression. So we have our f of x given, and we have x equals 3, which is like our a. So the required line will be given by y equals f of a plus f prime of a into x minus a, like you already saw over there. So and a now is 3. So f of x is 1 over square root of 1 plus x, which is the same thing as 1 plus x raised power minus 1 over 2. And I already taught you a sharp way of differentiating this. Bring down the power, which is minus half. Then differentiate inside the bracket. Differentiate 1, that's 0. Differentiate x, that's 1. So this is like half times 1. Then the original expression, leave it there, and then reduce the power by 1. So you have minus half minus 1 over 1. That's simply minus 3 over 2. So that's why you have what you have here. So you see f prime of x is equal to minus half into 1 plus x divided by the 1 plus x minus 1 over 2 into 1 plus x raised to the power minus 3 over 2. And that leads to this expression. So minus 1 over 2 into cube root of square root square root of 1 plus x raised to power 3, like this. So now that is your f prime of x. You know, from in this expression, you need f of a, you need f prime of a, and you need x minus a. So what is your f of a? So this is your f of x. So just put 3 here, and that is your f of a. So f of a is equal to f of 3. So put 3 here directly. So you have 1 into square root of 1 plus 3, and that is square root of 4, which is 1 over 2. So f of a is 1 over 2. And the next thing you need is f prime of a. So you see, you need f, this is f prime of x. So f prime of a would be f prime of 3. That means anywhere you see x, put 3. So you have 1 over minus 1 over square root of 2 into square root of 1 plus 3 raised to power 3. So, you know, square root of 1 plus 3 is square root of 4, which is 2. 2 raised to power 3 is 8. 2 times 8 is 16. So f prime of a is actually minus 1 over 16. So you have the f of a you need here. You have f prime of a that you need. You also need x minus a for you to get the complete expression. So we go and complete that in the next slide. So now we have y equals f of a plus f prime of a into x minus a. So f of a is half. F prime of a is 1 over 6. Then you have x minus 3. So in that case, you have 1 over 2 minus, expand this now, you have minus 1 over 16x plus 3 over 16. And then you can add 1, 1 over 2 plus 3 over 16. LCM again is 16. 2 in 16 is 8. Plus 16 is 16, 1 times 3, 3. So you have 11 over 16. So you see, this and this gives you 11 over 16. Then you have minus 1 over 16x. So now this is the linear approximation for that nonlinear expression. You see, so at the end of the day, this expression is actually a line. So that is why it is called linear approximation or linearization. So you can now say 11 over 16 minus 1 over 16x linearizes that function you were given at x equals 3. Okay, so let's take another example involving trig expressions. So with this linearization, now you can actually do this for any kind of expression, whether they are polynomial or not, whether they are transcendental like trig, inverse trig, exponential, logarithmic, or anything. You can actually linearize them using this simple method of linear approximation. So find the linearization of f of x equals e raised to power x sine x at x equals pi over 2 in radians. So again, this is what we always invoke. The required line is given by y equals f of a plus f prime of a into x minus a, where a now is pi over 2. So, f of x is e raised by x sine x. So if you differentiate that now, you have to use quotient rule. So you have u dv dx, which is differentiate sine x, that's cos x, plus plus v, which is sine x, du dx. If you differentiate e raised by x, you still get e raised by x. Sine x now remains what it is. So if you factorize e raised by x, that's why you have e raised by x into cos x plus sine x. So that is your f prime of x. That's f prime of x. So now it means f of a is f of pi over 2. So put pi over 2 for x. So here you have e raised by pi over 2. Then cos pi over 2. Cos 90 degrees is 0. And sine 90, pi over 2 is 90 degrees. Pi over 2 in radians is 90 degrees, right? So cos 90 degrees is 0 plus, so this is 0 now, plus sine 90 degrees is 1. So you have 0 plus 1. So it's more like you have e raised by pi over 2 multiplied by 1. And that's what, okay, you have sine pi over 2, and that's e raised by pi over 2 times 1. And that is why f of a is e raised by pi over 2. So you have that sorted. And then again, you need f prime of a. So that means you substitute pi over 2 here again. And of course, you already know that. Okay, what did I even do here? Sorry. F of a should be e raised by x sine pi over 2. Sorry. So this leads to this. Sorry, that was a mistake. So you have e raised by pi over 2 sine pi over 2. Sine pi over 2 is 1. So 1 times e raised by pi over 2, that you have e raised by pi over 2. Now, f prime of x is e raised by x cos x plus sine x. So that is what you bring here. So you have e raised by pi over 2, cos pi over 2 plus sine pi over 2. Cos pi over 2, that's cos 90 degrees, that is 0. And then sine 90 degrees is 1. So 0 plus 1 is 1 times e raised by pi over 2. So for both f of a and f prime of a, that is f of pi over 2 and f prime of pi over 2, you get both to be e raised power pi over 2 apiece. You get each of them to be e raised power pi over 2. So you can now bring your expression again. Y equals f of a plus f prime of a into x minus a, basically. So f of a is e raised power pi over 2. F prime of a is e raised power pi over 2 again. Then x minus a, that's x minus pi over 2 here. So we can tidy things up now. So you have e raised power pi over 2 plus e raised power pi over 2 multiplied by this. So we can factorize. You have e raised power pi over 2 here. Then divide this by e raised power pi over 2, divide by e raised power pi over 2. So you have so from here, once you've taken it out, you have 1. And once you've taken this out, you have x minus pi over 2 left there. So you have e raised power pi over 2 into 1 plus x minus pi over 2. So you can do this 1 over 1, 1 over 1 minus pi over 2. LCM is 2. So 1 into that's 2 minus pi. So this is like x plus 2 minus pi over 2, like that. So you can simply say then that e raised power pi over 2 into x plus 2 minus pi over 2 linearizes f of x equals e raised power x and x at x equals pi over 2. And with that, we've come to the end of application of differentiation to linear approximation. Thanks for listening. If you have not subscribed, don't forget to do that. So that and also click the notification bell so you don't miss any of the videos that will come your way later on. Thank you. See you in the next video where I talk about application of differentiation. So I think that should be rate of change. Thank you.